The big question for this segment is, how complex was the universe just after the Big Bang, and what forms of complexity were there? Our knowledge of the very early universe is uncertain, hidden behind a wall of flame beyond which we cannot see. It becomes increasingly difficult to see the early universe before 380,000 years after the Big Bang. Though with the beginning of our investigation into gravitational waves, we may someday see beyond that wall of flame to the earliest moments of the cosmos. But all the cosmological data so far collected paints a fairly reliable picture: a hot and dense universe expanding, growing cooler, and less dense over time. This had a profound effect on complexity. For frame of reference, computer modeling and mathematical calculations have shown that in the first fraction of a second of the universe's existence, that the bubble of the cosmos was about 1 trillion times 1 trillion times 1 trillion more dense than water. It was also about 10 to the power of 21 Kelvin. That's a 1 with 21 zeros, whereas water boils at just 373 Kelvin. That's quite a thick and piping hot bowl of primordial soup. Even the surface of a star is not nearly that hot, clocking in at a few thousand Kelvin. Within that soup, what sort of chunks of complexity do we find? In the first few seconds, almost none. The most basic tiny particles just emerging. There are about 200 elementary particles known to science. Of these, the collection of quarks, the ingredients for the protons and neutrons of atoms, were not able to come together in that intense fireball to form more complex structures or systems. Without the ability of building blocks to come together, you can't really have structures through which energy can flow. Without flow of energy, you don't really have any complexity. After the first few minutes, quarks formed protons and neutrons, and in turn protons and neutrons began to form the nuclei of atoms. This is because of the expansion of the universe, which made the first real complexity possible. Over the next few centuries, the universe cooled to a temperature and density comparable to most stars today. Nevertheless, because matter and radiation were so intimately coupled, the early universe remained a uniform, highly structureless blob. Not a lot of energy flow, not a lot of structure, not a lot of complexity. The reason why the early universe was so hot is because of pressure. Throw all the ingredients of the cosmos into a concentrated heap, and heat is generated. The same goes, to a much lesser degree, for the massive clumps of hydrogen and helium gas that form a star, or the molten core of a sufficiently large planet like Earth. But then, let us back up. Why did any complexity emerge in the universe at all? Why wasn't the universe stillborn, uniform, dead, at equilibrium, without any future for complexity in the cosmos? Well, at approximately 10 to the power of negative 35 seconds, at the quantum scale, there were tiny particles popping in and out of existence, just as there are the same virtual particles bubbling in the room you are sitting in right now. Usually these virtual particles are too small to have any impact on the universe at larger scales. But during the earliest phases of cosmic inflation, the universe started from small enough a size, much smaller than an atom or even a quark, that these quantum variations were able to have an impact, and these variations suddenly were writ large when the universe became the size of a grapefruit in the fraction of a blink of an eye. The writing these fluctuations left on the cosmic wall, still visible in the picture of cosmic background radiation, created minute variations in the distribution of matter and energy in the universe. Those tiny footprints at the quantum scale are responsible for all the increasing complexity that followed in the next 13.8 billion years. We owe our entire story to them. In time, those tiny variations were to clump together hydrogen and helium in stars, which in turn produced chemical elements, planets, and us. All that came from a tiny blip that happened in a sliver of a second at the beginning of space and time. Over the next 3 minutes, the universe cooled to the point that quarks formed into protons and neutrons, which in turn formed the nuclei of hydrogen and helium that make up the vast bulk of atomic matter in the universe. This laid the groundwork for most of the heavier elements that would form in the bellies of stars and the firestorms of supernovae. Then, after another 380,000 years, the universe expanded further and cooled to a balmy 3,000 Kelvin. At these temperatures, radiation was able to travel more freely, racing out in a blinding flash, leaving matter to grow more dominant and capture electrons, becoming fully fledged atoms. Even then, we are talking the simplest of all elements, hydrogen and helium, making up the overwhelming majority of matter in the early universe. In terms of building blocks, they are pretty simple. A hydrogen atom is made up of 1 proton and 1 electron. Helium is slightly more complex, in a grouping of 2 protons, 2 neutrons, and 2 electrons. But compare that to iron, the heaviest element forged in the belly of a star, which is 26 protons, 30 neutrons, and 26 electrons. When stars go nova, they produce elements like gold, 79 protons, 118 neutrons, 79 electrons, and uranium, 92 protons, 146 neutrons, and 92 electrons. But these would need to wait for the explosive firestorms of supernovae in order to form. All told, the early universe was not a very complex place. Not, at least, until gravity capitalized on minute inequalities in the distribution of hydrogen and helium atoms, sucking them into deeper and deeper concentrations, until the heat and pressure built up so much that the first stars flared into life, and the universe got a little warmer once again. Even then, these first stars were not very complex structures. The density of energy flows in your average star is many hundreds or even thousands of times lower than the density of energy flows in a living organism. They are also structurally simple, great lumps of pressurized hydrogen and helium with trace amounts of other elements. They were, however, the first complex systems in a universe that was rapidly cooling to only a few degrees above absolute zero, and a universe that is 99.99999% space. But this was the universe's first attempt to claw a little further away from total uniformity and simplicity. Stars were the first structures through which energy could flow in a complex system, and as a result, produced the atomic structures that yielded organic chemicals, life, and us. The rest, as they say, is history.